In the ninth lecture, we will cover the type 1 and the type 2 error, power of a test, and the hypothesis test for proportion. In hypothesis testing, a type 1 error is the rejection of a true null hypothesis, also known as false positive, while a type 2 error is the failure to reject a false null hypothesis, also known as false negative. The probability of making a type 1 error is represented by the significance level alpha. If alpha is 0.05, then there is a 5% chance that we reject the true null hypothesis. The probability of making a type 2 error is called beta, which is the chance that we fail to reject a false null hypothesis. 1 minus beta is the power of the test. The probability that the test rejects the null hypothesis when the alternative hypothesis is true. The following table shows the testing results crossed with the true results. When the null hypothesis is true, if we fail to reject the null, then it is true negative, and the chance is 1 minus alpha. If we reject the null, then it is a false positive as a type 1 error, and the chance is alpha. Here, positive is the test result, and false tells us the test result is false. When we fail to reject the false null hypothesis, we have a false negative as a type 2 error, and the chance is beta. If we reject the false null, then it is true positive, and the chance is 1 minus beta, which is the power of test. Let's use this right graph to understand the trade-off between type 1 and type 2 error. The example is a right-tailed test. The upper graph shows the distribution when the null hypothesis is true. The lower graph shows the distribution when the null hypothesis is false. Since the test is right-tailed, the parameter is larger than the null value when the null hypothesis is false. Thus, the lower graph is positioned further right to the upper graph. The significance level alpha makes the area that we make a type 1 error in the up graph. The red dashed line is the delimiter of the conclusion. If the test statistic is to the left of the line, then we fail to reject the null. If it is to the right of the line, then we reject the null. In the lower graph, the null hypothesis is not true. Beta is the area that we fail to reject a false null as the type 2 error. 1 minus beta is the area that we reject a false null because it is right to the red dashed line. If we increase alpha, for example, from 0.05 to 0.1, the red dashed line will shift left. Type 2 error beta will decrease, and the power of test 1 minus beta will increase. Also, if we decrease alpha, for example, from 0.05 to 0.01, then the red dashed line will shift right. Type 2 error beta will increase, and the power of test 1 minus beta will decrease. Since type 1 and type 2 error adversely affect each other, there is a trade-off between them, and we need to balance these two errors. Let's use one of the previous examples to understand the power of the test. A school would like to know the average SAT score of the admission applications. The research hypothesis is the average score is less than 1,000. The sample of 100 applications has an average score of 964, and the sample standard deviation is 200. From the last lecture, the test statistic z-score is minus 1.8, and the p-value is 0.036. Thus, we reject the null hypothesis and conclude that the average SAT score of the past applications is less than 1,000. Now the question is, how powerful is this rejection? As we already know, the test is a left-tailed test. At the 5% significance level, we will reject the null if z is less than minus 1.645. Thus, the red dashed line is at z equal to minus 1.645. Now let's find the critical sample mean, which is the maximum sample mean that we may reject the null hypothesis. This equation gives the critical sample mean is 967.1. If the sample mean is less than 967.1, then we will reject the null. Power is the probability of rejecting the null when in fact it is false. We have a sample mean of 964, and it is less than 967.1. Thus, we believe the alternative hypothesis is true. Since the average SAT score is 964 in our example, the sampling distribution would be a normal distribution with mu 964 and a standard error of 20 when the null hypothesis is false. Power is a proportion of y bar less than 967.1 conditional on H1. The corresponding z-score is z equal to 0.155, and the power is 56.2%, and the type 2 error is 43.8%. Again, we emphasize that the power of the test is based on the rejected null hypothesis. If no significance is found and we fail to reject the null hypothesis, then we cannot define the power of the test. The example here shows it has a power of 56.2%, which doesn't seem very high. So how do we increase the power? In the last slide, we learned we may increase the significance level to increase the power. In this example, if we increase alpha from 0.05 to 0.1, then the red dashed line will shift right and the power will increase. But often we do not prefer to increase the significance level because alpha is the type 1 error rate. Alternatively, we may increase the distance between mu0 and mu1 to increase the power. In the example, we may increase mu0 from 1000 to, say, 1100. However, 1000 is our target score, and 1100 may not be our research interest. On the other hand, mu1 is determined by the sample, and it is fixed when we have the sample. At last, we may increase the sample size. This may increase the power and at the same time keep the significance level intact. Here, let's try to find the minimum sample size required to have a power of 80% and a significance level of 5%. For the left-tailed test, 80% power leads to a critical z-score of 0.842. From the Excel function norm.s.inverse. Z beta gives the required power level, and Z alpha gives the 5% significance level. So we have the following two equations. We combine these two equations into one and have the formula for the sample size for a one-tailed test. Here, the test is left-tailed. Thus, Z alpha is less than 0 and mu1 is less than mu0. In the end, we have the minimum sample size 191. We need at least 191 applications to have an 80% power. Of course, if we have such a sample, the sample mean may change too. Thus, the test power may not be 80%. We flip a coin 100 times and get 60 heads. At the 10% significance level, can we get to the conclusion that the chance of getting the head or tail is not equal? We have a random sample of size 100. And the sample proportion is 0.6. The null hypothesis, the chance of getting the head and the tail is equal. So P is equal to 0.5. Under the alternative hypothesis, P is not equal to 0.5. Under the null hypothesis, the population proportion is 0.5. The similar problem has been reviewed when we studied the confidence interval. There is an interesting difference between the confidence interval estimation and the hypothesis testing for proportion. In hypothesis testing, we assume the null hypothesis is true, and we may set the population proportion in the null hypothesis. But we lack the information of the population proportion when we calculate the confidence interval, and we may have to estimate it using the sample proportion. Here, we should not use the sample proportion since the null hypothesis already sets P equals to 0.5. Both NP and N1 minus P is 50, greater than 10. Thus, the null distribution is approximately normal. The standard error is square root of P1 minus P divided by N, which is 0.05. The test statistic z-score is P hat minus P divided by the standard error, which is 2. The p-value is the proportion of the null distribution more extreme to the z-score, which is 2 times of 0.023 for a two-tailed test. Since p-value is 0.046 less than 0.1, we have enough evidence to reject the null hypothesis at the 10% significance level and conclude the chance of getting the head is higher than the chance of getting the tail. Now let's calculate the power of the test for this example. At the 10% significance level, we may reject the null if z is less than 1 minus 1.645 or z is larger than 1.645 for the two-tailed test. Thus, we have two critical sample proportions. the maximum sample proportion in the left tail and the minimum sample proportion in the right tail. The left critical sample proportion is determined by a z-score of minus 1.645, and the right critical sample proportion is related to the z-score of 1.4645. The population proportion is 0.5, so the left critical sample proportion is 0.5 minus 1.645 multiply the standard error and yield 0.42. And the right critical sample proportion is 0.5 plus 1.645 multiply the standard error, and we have 0.58. The right graph shows two red dashed lines instead of one because the test is a two-tailed test. The power of the test is the sum of the two conditional probabilities. The graph below shows the distribution when the null hypothesis is false and the estimated population proportion is 0.6 instead of 0.5. Type 2 error occurs when the test statistic falls in between the two dashed lines because we cannot reject the null even the null hypothesis is false. The area in the left tail is very small and corresponds to the first term, p z less than minus 3.645, and the probability is only 0.13%. The area right to the right dashed line corresponds to the second term, p z is greater than 0.36, which is closer to 64%. The sum of these two is the power of the test, still 64%. It seems that we may safely ignore the area in the left tail since the result is the same, but it may not always be the case, especially when we have a larger standard error. It is best to include both regions for the two-tailed test. In summary, we learned the type 1 and type 2 error, power of the test, and the hypothesis test for proportion in this lecture. A type 1 error is the rejection of a true null hypothesis, also known as false positive, at the significance level alpha, while a type 2 error is the failure to reject a false null hypothesis, also known as false negative as beta. The power of test is the probability that the test rejects the null hypothesis when the alternative hypothesis is true as 1 minus beta. Type 1 and type 2 error adversely affect each other, and there is a trade-off between the two errors. We need to balance these two based on our interest. We may increase the power of test several ways, such as the increase of the significance level, the distance between mu0 and mu1, but most practically through the sample size increase. For a one-tailed test, the minimum size required to have the specified power may be calculated by this formula.